deep dive into something pretty amazing.
Yeah.
It's a question you might not even have thought to ask.
Okay.
Where did the heaviest elements in the universe come from?
Okay.
You know, stuff like gold and platinum.
Right.
Even uranium.
Uh-huh.
Turns out it's a story way more intense than just stars and supernovae.
That's right.
So today,
Yeah.
we'll be tracing the journey of elements from the Big Bang to some seriously mind-blowing events to understand how those heavy hitters were formed.
Yeah.
It's complex stuff, but don't worry.
Right.
We'll make it clear and fascinating.
Okay.
I've got an expert in astrophysics with me today, so we're in good hands.
Wonderful.
So to get us started, can you tell us just a little bit about your background and kind of how you got into this field?
Oh, sure. So, I've always been fascinated by like the really big questions, like where did we come from and what is the universe made of and are we alone? And so naturally I was drawn to astrophysics because it tackles those questions head on. And what captivates me about the heaviest elements, like the ones we consider precious or even dangerous, is that they're really testaments to the universe's most extreme processes, events so powerful. They literally warp the fabric of space-time.
Wow.
It's pretty amazing.
Okay, so we know that the Big Bang created hydrogen and helium, the lightest elements.
Yeah.
Why couldn't it just keep going and create everything else?
Yeah, that's a great question.
That was a pretty intense event, right?
Yeah, it was, but it gets to a crucial point. The early universe, while energetic, had a bottleneck.
Okay.
Imagine a cosmic traffic jam where every time a deuterium nucleus tried to form, it was immediately smashed apart by these high-energy photons.
Okay.
So deuterium is just a proton and neutron combined.
Okay.
And this is what we call the deuterium bottleneck.
So even in the Big Bang, there were limits. It wasn't just everything was created at once.
Exactly. By the time the universe had cooled enough for deuterium to survive, things had spread out too much.
Oh, okay.
The density had dropped, which is key for those atoms to bump into each other and fuse into heavier elements.
Got it.
So the Big Bang produced hydrogen, helium, a smidge of lithium, and that was it for a while.
Wow. Okay, so where do stars enter the picture? I'm guessing they're not just twinkling up there for fun, right?
No, they're not. They're the universe's element factories. But even they have specialties.
Okay.
Take our sun, for example.
Yeah.
It spends most of its life fusing hydrogen into helium. That's its main gig. And it does it well.
So like a giant cosmic power plant just chucking along.
Yeah, a perfect analogy, but massive stars.
Yeah.
Much larger than our sun.
Oh,
Those are where things get more interesting.
Okay.
As they run out of hydrogen, their cores contract and heat up, allowing them to fuse heavier elements.
Okay.
Think of it like building the periodic table in layers, like an onion.
Okay.
First, helium fuses into carbon and oxygen. Then carbon fuses into neon and magnesium and so on.
So wait, silicon fuses before oxygen? That seems kind of counterintuitive.
The universe plays by its own rules.
Yeah.
This process is called the THES process,
Okay.
which stands for slow neutron capture.
Got it.
And it's where free neutrons, produced as byproducts, get captured by existing nuclei, building up heavier elements.
Okay.
However, even massive stars hit a wall when they reach iron.
Okay.
Fusing iron actually consumes energy instead of releasing it.
Oh, wow.
And that's where things start to get.
So that's where we get to the big dramatic events, right?
Yeah.
The star goes supernova. Does that forge those super heavy elements?
It's true that supernovae are incredibly energetic.
Yeah.
But even they have limits when it comes to creating the heaviest elements.
Really? I thought they were the ultimate cosmic explosions.
Yeah.
What's the catch?
The catch is in the specifics of how elements are made.
Okay.
Supernovae are great at the R process, or rapid neutron capture. Imagine a neutron blizzard where nuclei are bombarded with neutrons so rapidly they bulk up, forming elements up to rubidium in abundance.
Okay.
But that's where it fizzles out for the ART process.
Okay.
Even those super bright type ES supernovae, while powerful, don't create the conditions for the really heavy elements.
So if not supernovae, where do gold, platinum, and those ultra-heavy elements like uranium come from?
That's where things get really interesting.
Okay.
We have to turn to the densest objects in the universe, neutron stars.
Okay.
And a phenomenon so extreme, it makes a supernova look like a sparkler.
Okay, now I'm intrigued. Neutron stars, what happens to them?
Imagine two neutron stars,
Okay.
remnants of massive stars that have collapsed, to an unimaginable density locked in a death spiral.
Okay.
As they draw closer and closer,
Yeah.
they warp space-time itself until they collide.
Oh, wow.
And that, my friend, is a kilonova.
Two neutron stars colliding. That has to be one of the most powerful events imaginable, right?
You're not wrong.
Okay.
It's in kilonovae.
Yeah.
These cataclysmic events where the real heavy metal magic happens.
Okay.
We're talking an insane amount of free neutrons released, driving the R process into overdrive.
Wow.
Forging elements like gold, platinum, uranium, and even heavier elements like plutonium.
Hold on. So the gold in my ring, the platinum in a catalytic converter, that all came from these ridiculously violent neutron star collisions?
Most likely.
That's incredible.
And the story gets even more exciting.
Okay.
In 2017, we had the first confirmed observation of a kilonova.
Oh, wow.
Gravitational waves.
Yeah.
A gamma ray burst. Light across the spectrum.
Wow.
It was like the universe put on a show to confirm what we suspected.
That's amazing.
And guess what? We detected the signature of newly formed heavy elements.
Well, talk about confirmation, but if these kilonovae are so crucial for heavy elements, shouldn't we see more of them?
That's the mystery. Okay. The frequency of kilonovae we've observed doesn't quite explain the abundance of those heaviest elements in the universe.
Really?
So it begs the question, is there another source we haven't discovered yet? Another type of cosmic factory out there churning out these heavy elements?
All right, now that's a cliffhanger. I guess we'll have to dive into part 2 to uncover more of these cosmic secrets.
Sounds good.
All right, we'll be right back after a short break. Welcome back to our deep dive into the origins of heavy elements. Before the break, we were left with a pretty tantalizing question. Are there other sources of heavy elements besides kilonovae?
Yeah.
It seems like we've only just begun to scratch the surface of this cosmic mystery.
You're right.
So what are your thoughts?
Well, you're absolutely right. The universe is vast and full of surprises, and while kilonovae are incredible sources of heavy elements, the story doesn't end. There are a few other contenders vying for a spot in this element-creating saga.
Ooh, love a good cosmic competition. Tell me more about these other potential heavy element factories.
Okay, well, one intriguing possibility involves a phenomenon known as a collapser.
Collapsers?
Yeah, picture a star
Okay.
so massive that when its core collapses, it doesn't just form a neutron star.
Okay.
It keeps collapsing all the way down to a black hole.
With black holes as element factories? Now that's a mind-bending concept.
Yeah.
How could something that swallows everything create anything?
It is pretty wild. The idea is that as the black hole forms, it's surrounded by this swirling disk of superheated matter.
Okay.
This disk, a maelstrom of particles and energy, could have conditions extreme enough to trigger the R process on a colossal scale.
So it's like a kilonova.
Yeah.
But with a black hole at the center, amplifying the chaos and churning out even more heavy elements. That's intense.
That's a great way to visualize it.
Wow.
It's still theoretical, but some simulations suggest that collapsers could be powerful enough to produce significant amounts of heavy elements, maybe even explaining some of the rarest, most radioactive elements that we're still struggling to account for.
So collapsers are one contender. Are there any other possibilities in the running for these missing heavy element sources?
Remember those type Ia supernovae we discussed earlier? The ones where a white dwarf star explodes?
Yes.
While they're not typically known for heavy element production,
Right.
there's a chance they might contribute more than we initially thought.
Okay.
Under very specific circumstances.
I'm all ears. What kind of specific circumstances are we talking about? Does this involve those white dwarfs stealing material?
Exactly. If a white dwarf accretes enough material from a companion star, or even merges with another white dwarf, it can become incredibly dense and hot before it finally explodes.
Wow.
And some models suggest that these extreme conditions could allow for a limited R process to occur, producing some heavier elements.
So it's like a souped-up type Ia supernova, pushing the limits of element creation.
Precisely. It's still an active area of research, and we need more observations to confirm whether these special type Ia supernovae are significant contributors to heavy element production or just minor players in the grand scheme of things.
So it seems like there's so much more to uncover about how the universe creates these heavy elements.
Absolutely.
We've come a long way from thinking that supernovas were the sole source.
Right. The more we learn, the more we realize how complex and interconnected these processes are. It's like a cosmic puzzle, and each new discovery adds another piece to the intricate picture of element creation.
And speaking of the bigger picture, is the distribution of these elements uniform throughout the universe? Or are there some areas richer in heavy metals than others?
That's a fascinating question, and the answer is no. The distribution isn't uniform. We see variations in the abundance of heavy elements depending on where we look in the universe.
So some galaxies are basically heavy metal havens. That's wild. What causes these variations?
Yeah. These variations are like cosmic fingerprints, telling us about the history of star formation in different parts of the universe. Galaxies that have experienced more generations of stars, more supernovae, and kilonovae will generally have a higher proportion of heavy elements.
So it's like cosmic archaeology. We're using the elements as clues to piece together the history of galaxies. That's amazing.
Precisely by studying the abundance of elements in different stars and galaxies, we can trace the evolution of the universe itself, from the first stars to the formation of planets like our own.
And this is where it gets really personal, right? Those heavy elements forged in stars and kilonovae, those are the building blocks of everything around us.
Absolutely. Think about it. The iron in your blood, the calcium in your bones, the gold in your jewelry, all of it originated in these incredible cosmic events billions of years ago.
Wow, it's mind-blowing to think that the atoms making up our bodies were once part of stars and neutron star collisions. It makes the saying, "we are stardust," so much more profound.
We are indeed, and that realization, I think, is one of the most profound insights astrophysics offers us. It connects us to the universe on a deeply personal level, reminding us that we are not separate from the cosmos, but rather an integral part of its ongoing story.
Okay, I'm officially in awe. But before we get lost in the existential wonder of it all, I have a more practical question. We've talked about how heavy elements are made, but how do they actually get distributed throughout the universe? I mean, a kilonova happens way out there. How does that gold end up on my finger?
That's a fantastic question. It brings us to another captivating aspect of cosmic element synthesis, the role of interstellar gas and dust.
So we're talking about the stuff that floats between the stars, the cosmic fog.
Exactly. The interstellar medium, think of it as the universe's recycling bin when stars explode or neutron stars collide. They eject these newly formed elements into space. This material mixes with the existing interstellar gas and dust, enriching it with heavier elements.
So it's like a cosmic soup getting richer and more flavorful with each supernova and kilonova.
I love that analogy. Over time, this enriched interstellar medium can clump together under the force of gravity, forming new generations of stars and planets.
So the gold in my ring was probably once part of a neutron star collision, then floated around in space for a while, and eventually got incorporated into the Earth as it was forming.
That's the most likely scenario. It's an incredible journey, isn't it? From the heart of a dying star or the cataclysm of a kilonova to the palm of your hand.
It really is.
Yeah.
It makes you realize that the universe isn't some distant, abstract entity. It's intimately connected to everything we are and everything we experience. Well, I think we're ready to wrap this up. Let's dive into the final part and see what other wonders await.
Sounds good.
Welcome back to our deep dive into the world of heavy elements. We've journeyed from the Big Bang's first whispers of creation to the mind-boggling violence of neutron star collisions. It's been a wild ride. But before we wrap up, I have to ask, what does this all mean for us here on Earth? Why should we care about where gold or uranium or any of these elements come from?
You know, it's easy to get caught up in the cosmic scale of it all. But the impact of these events is surprisingly personal.
Right.
Those heavy elements forged in the hearts of stars and the chaos of kilonovae, those are the literal building blocks of our world, of you.
So without those seemingly distant explosions and collisions, our planet wouldn't even exist. And life itself, that wouldn't be possible either.
Exactly. Imagine a universe without heavy elements. No rocky planets like Earth. No carbon for the complex molecules that make up life as we know it. No oxygen to breathe, no iron for our blood. It's a pretty bleak picture, isn't it?
Definitely puts things into perspective. It's not just about pretty jewelry or powerful energy sources. These heavy elements are fundamental to our existence.
We are quite literally children of the cosmos, shaped by elements forged in the fiery crucibles of stars and the unimaginable chaos of neutron star collisions. It's a humbling thought.
It makes that phrase, "we are stardust," feel so much more real and profound, not just a poetic idea, but a scientific reality.
It is, and for me, this understanding shifts how we see our place in the universe. We're not separate from these grand events, we're a product of them, a continuation of their story.
It really highlights the interconnectedness of everything, doesn't it? This incredible cycle of creation and destruction constantly reshaping the universe and, in the process, giving rise to complexity in life as we know it.
Absolutely, and this understanding has practical implications too.
Okay.
By studying the distribution of elements in stars and galaxies.
Yeah.
We gain insights into the history of the universe, how galaxies evolve, even how planetary systems form.
So it's not just about knowing where gold comes from. It's about using that knowledge to understand the bigger picture, The grand story of the universe itself. It's like cosmic detective work.
Exactly. And as we develop even more powerful telescopes and instruments, who knows what else we'll discover, we'll be able to delve deeper into these mysteries, uncover new insights into the origins of the elements, and understand the intricate processes that govern the cosmos.
It's amazing to think that even something as seemingly simple as a gold ring holds a story that stretches back billions of years, connecting us to the most extreme events in the universe. It's a reminder that even the most familiar things can be incredibly profound when we look at them through the lens of science.
I couldn't agree more. The universe is full of wonder and beauty waiting to be discovered.
Yeah.
All we have to do is keep asking questions, keep exploring, and keep our minds open to the endless possibilities that lie ahead.
Well said. A huge thanks to you for guiding us through this incredible deep dive into the origins of heavy elements. It's been an absolute pleasure.
The pleasure was all mine.
And to all of you listening, thanks for joining us on this cosmic journey. Until next time, keep looking up and keep those minds curious.